raging of electrons. A rage bit, not bad.
All right, you should be on the back side of the first page. Can you flip there, please? Okay, we're going to take some general notes. So if you can get there, please, I'd appreciate it. The talking needs to come to an end.
Which one?
We're going to write down the, fill in some notes here.
Where at?
Okay, so we're on page 2. Page numbers are at the top, and you're going to finish up that sentence. Light is a kind of electromagnetic radiation.
Oh, I got it. Do you like it yet? Sorry.
Focus.
Where do we put the bullet points at?
You don't need a bullet point. We're just going to talk about it. Okay? Okay, electromagnetic radiation, guys, is going to be part of the... You guys have heard of Roy G. Biv before, right? Middle school, elementary school, the rainbow colors, right?
Yeah.
So electromagnetic radiation is visible light, which is Roy G. Biv, is part of that thing. So is UV light, so is infrared light, so is X-rays.
So it's all part of the spectrum.
It's all part of the electromagnetic spectrum, right? So then we're going to look at parts of a wave, okay? Now, parts of the wave, we have the wavelength. It's distance from crest to crest or trough to trough. And if you think about what a wave looks like, so here is a wave, right? Crest to crest would be here, right? That's a wavelength. That distance is a wavelength. Okay, so right here is a wavelength. Or I could go from trough to trough, which is the same thing. It can be crest to crest or trough to trough. Now we use the symbol lambda, which looks like an upside down Y turned backwards, kind of, right? When I draw it with a stick, when I draw it, I make it look like that. I'm not that fancy. That's just right off the thing. So that's the symbol lambda. It's a Greek letter. So a wave like this is the distance from crest to crest. Frequency is the number of waves that passes a given point. So how many times does that wave pass a point? We measure that in something called hertz. Okay, 4 cycles per second. And we use the Greek letter nu for that. It's kind of a fancy V. When I draw it by hand, because I don't have, a font, and I have horrible handwriting, you will see me draw my nu like that. And then amplitude is the distance from origin to crest. We're going to draw a wave in a moment and label its parts anyway, but I want you to have the definition. So take a moment to get these definitions copied down. All right, so you have on your sheet already the speed of light, 3.0 times 10 to the 8th meters per second. Remember, a meter is about the tip of my nose. Well, from the tip of my nose to the stretch of my finger is about 88 centimeters. So add another 12 to that, centimeters, and that's about a meter. So remember, this times 8 number here says to move the decimal 8 times to the right. So that's how many meters per second light travels at. You should have that number written in your notes already, am I right?
Yeah.
Okay, and then you just need to write the formula. C equals, that means the speed of light, equals wavelength times frequency. Remember, that lambda symbol is wavelength, and that nu symbol is frequency. All right, parts of a wave. So I want you to draw this page here and label the parts. Right there where I left that blank space in about the middle of page 2. So take a moment to draw the wave diagram. This next slide we're going to look at, these are a couple different wavelengths here. Okay, this is red light. So that wavelength there that you see on top represents red light. This would represent a yellow-green light or a violet or purplish colored light. So you can see, remember the wavelengths are from crest to crest or trough to trough. And I'd like you to take a moment to rank the colors. So right down here you're going to put either R, Y, G, or V. You're going to rank them from longest to shortest. From longest wavelength to shortest. Remember what wavelength is? It's this distance from here to here, or from here to here, or from here to here, right? That's a wavelength. So by color, rank them from longest wavelength to shortest wavelength. Frequency to small. So what's my longest wavelength? What color?
Red.
Red. And then what was next?
Yellow, green.
Yellow, green,
Violet.
and violet. Now, what about greatest frequency to smallest frequency?
Violet.
It's backwards, right? Violet, yellow, green,
red.
and red. If you look at these, right, if you look at violet, it's got a lot more crests that are coming across in the same amount of time, that we were saying that this was the same time frame. Does anybody know what we call this concept when it increases one thing for one thing but decreases for the other? Meaning, how are these related? What's that term for how they're related? Anybody have an idea of a term for how they're related? Let me give you the two words and pick from them. Are they directly related or indirectly related? Indirectly. In other words, another way we could say it is they're inversely related. Inverse means the opposite, right?
Yeah.
Opposite's not a great word. Okay, but reverse it, right? Flip it. What's the inverse of 10? In math class, what's the inverse of 10?
-2.
No.
0.
No.
Oh, never mind.
Anybody know what the inverse of 10 is? 1 over 10, right? What's the inverse of 1/5? Flip it. 5, right? Okay. So that means frequency and wavelength are inversely related. Okay, and I believe that's what we're going to write down there. We're going to write down these 4 bullet points. So, nothing to write down for this slide. But in order to understand electrons, remember what the electrons are. Electrons are in the outside, what we call the energy levels, or the electron cloud. We have to understand how light and electromagnetic waves work. Okay, and that's what we're getting into here. All right, so you have in this diagram, you have parts of this. You have the actual spectrum here. But I want you to add some, and obviously yours is not in color because this is black and white copy. But I want you to add the low energy, low frequency, and long wavelength on the left, and add high energy, high frequency, short wavelength on the right. So take time to do that. I will fix. All right, so anything that, for instance, radio waves have low energy, low frequency, but they have very long wavelength. Remember, these were opposite each other. This is very long, okay, wavelength, which means it's low. Okay. All right, so we're not going to write anything for this. We're going to look at a prism. Hopefully you've looked through a prism before and you saw light broken down into a rainbow. Okay. So white light is made up of all the colors of the visible spectrum, the Roy G. Biv colors. We pass it through the prism, it separates out. Okay. So we can kind of use that concept to talk about things that are not white light. Okay. So something that is an element that has been, for instance, a hydrogen or a helium or a neon that has been charged with electricity, so its electrons are moving around, and this particular light comes in like a maroon color, whatever you want to call it, and it separates into that way. Okay, and that's how we get to what we call spectrum. Okay, and that's how we know what stars are made out of, what that elements are different because of their electron arrangement. So we have here, these are 3 different elements, okay, or a copy of. And years ago when I used to teach this class, when I first started teaching, we would have spectrophotometers, so a black instrument, plastic, hard plastic that had a piece of prism in it. We'd look at light and look through these different things like hydrogen, helium. We don't have that equipment. It's very expensive equipment. It's very outdated and it's old, so we don't have that. But what you would have seen as you peek through your black box, as you shine it on the light, different lights, as you would have seen different bands of color show up depending on what element we were looking at, what element was going through that gas discharge. You imagine for a moment it looked like a neon light, the tube from a neon light, and then you would shine your spectrophotometer on it and it would break apart the light. Okay, so now we're back into notes. So we have this thing called atomic emission spectrum, okay, and the absorption spectrum is what we're looking at here, and here we are, atoms of gas exposed about halfway down the page, atoms of gas exposed to electromagnetic radiation, electrons absorb the energy, so the electrons absorb energy, the words you're filling in are underlined in green, they become excited, we're halfway down this page, there you go. and they jump up to a higher energy level. So they jump up to a higher energy level. They gain enough energy to go into another level. You can kind of think of it as if they're standing on one ring and they jump up to the next ring, or they climb up to the next ring. Okay, I'm going to use that as an analogy. When that happens, we see something called the absorption spectrum. And I want you to describe this section this way. Colors absorbed shows up as dark bands. The colors absorbed show up as dark bands. So the colors that are actually absorbed are these dark bands. So there's some reds, some oranges, some yellows, some violets down there. Okay, so where it says describe the spectrum, you're writing this. Colors absorbed show up as dark bands because we don't have colored pencils and stuff to write. So these electrons gain energy, and in the case of the example I was showing you, okay, from the electricity I was pouring through them, they jump up, they become excited, they gain or absorb energy, become excited, and go to a higher energy level. Right? But they can't stay up there forever. Okay? Eventually they're going to lose that energy. They're going to fall back down. Let's see, let me hope you know all the words here. It just has this part right now. So here's my electron, and it's going to fall back down. So flip the page. The excited, so you're on page 4, the excited electrons lose or emit energy and go back to the lower energy level. I'm trying to see which words you need it right, or the ground state. Yeah, I didn't leave enough space, so I should have left you one more space. Should say lower energy level or ground state. So they gain energy, they jump up to an energy level, they fall back down, so you climb back down the ladder, what we call the ground state. When that happens, when they're coming back down to ground state, we have something very valuable. It's called the emission spectrum, or the bright line spectrum. This is where you're going to see colored bands. So for the description, you can just put colored bands. Colored bands of light, if you want to add that part. So remember the voids of the black spots? If I put these on top of each other, these colors would fill in, wouldn't they? Because that's about where they were. This is useful to us because we have different spectra for different elements. And that's how we see what stars are made of. Okay? So, let's see where we are. Elements give off their own characteristic color. We're about about a third of the way down the page. They can use to identify the atom. And this is how we know what stars are made of. Stars.
So is it the same thing for planets? Because I would.
Well, planets aren't going to. I mean, yeah, if they're radiating their energy.
I mean, I was just thinking
we
some of them are
mostly
gas giants and stuff. Because
well, and honestly, I am not good with astronomy, so I couldn't tell you more than this piece here.
I mean, I would figure.
Okay, so here we have, and I had to do some correcting to my PowerPoint, so I apologize. Ignore the stuff that I've X'd out. But it's sort of showing the whole process. You don't have anything that you're not going to draw the diagrams. It's just going through it visually with you. We're up here, right? As electrons absorb energy, they can move farther from the nucleus. So you're doing farther from. Okay. As they release energy, they move closer to the nucleus, and then you're doing all of this last part here. Meaning that they get closer to the ground, they get closer to the ground state or lowest energy level. So they gain energy and jump up, lose energy and fall back down. That's really what I want you to get out of what we've been talking about the last few minutes. They gain energy and they jump up energy level, and when they do that, they absorb some energy. When they fall back down, they release these bands of color. Okay? So fill in the blank, the words in the spaces. Everybody have it? What are we looking at time? Okay. So we have this diagram here, and what we have here is this electron gained energy, jumped up here, and as it falls down, it's given off these wavelength of light, and that's how we get those bands. And those bands help us to identify who's who. All right. Questions about that piece? So this is that same page we looked at where these are different bands of light, and then we'll get to the next piece here in a minute. Let me